implement. And it has some nice properties. So there are some languages that use a variation of mark and sweep garbage collection. So how does mark and sweep garbage collection work? So the idea behind it is we said that our goal was to uh, only garbage collect items that are not reachable from the root set. So how do we actually do that? Well, mark and sweep says, okay, let's actually just do the graph traversal to find all the objects that are reachable versus not, right? So we're going to go ahead and we're going to traverse A. We're going to say, okay, A is part of the live set, and what are all the things that it points to? Well, it points to B. So I'm going to put B on the to-do list, and then I'm going to go ahead and process the next element of my to-do list. So B is on the to-do list. So I process it. It has no outgoing fields, and then I am done. Right? I found every reachable object in my program. And then all I do is I just go over the heap looking for dead objects, and anything that's reachable, I unset its reachable bit, and anything that doesn't exist, I just go ahead and deallocate it. So that's why it's called mark and sweep. You first mark live objects, and then you sweep away the garbage. And one of the benefits of mark and sweep collection is that you don't actually have to move objects around. Objects stay in the same memory. So it's a good fit when you don't actually know where all the pointers are. For example, if you have some sort of FFI situation. And of course, we need a way to actually allocate objects that are free. And so typically all the elements that don't have objects in them get linked together using their space into a free list. So you can serve allocations from this free list. So that's not too complicated. So just to summarize, mark and sweep handle cycles, right? Because you'll just never reach a cycle. You never mark them and they get swept away. And you also don't need any extra bookkeeping for mark and sweep, right? You just, mark and sweep is a good algorithm if you're like trying to retrofit garbage collection onto some sort of system that didn't previously support garbage collection. Because all you really need is a way to like mark the objects as being live or not. Now, there are some problems. So there are two problems with the algorithm that I described here is that we had to traverse the entire heap to sweep things away. And we also, we never like moved objects around. So that can result in what's called fragmentation, where you have a bunch of objects sort of hanging out like at various points in your memory space. And then if you need a really big allocation, there's nowhere you can service it from because like every large chunk was like cut up by some object in question. Now there are ways to like deal with these problems with more sophisticated algorithms. For example, fragmentation, you can imagine having a compacting set which moves objects around to put them together in memory. But like the simple algorithm I get doesn't let you do that. And some other problems with mark and sweep that are more fundamentally algorithms. So you need a place to store the mark bit. So if you got a language where you don't actually, if you got a heap representation where you just don't have that space, that's a bit of a problem. Actually, if you've ever worked in a programming language where, actually that's not what the mark bit is used for there. So never mind. You also need to maintain this to-do list, right? Like this to-do list could grow arbitrarily in size as you're executing because, we're basically doing some sort of breadth first search on our program. So like you have to actually maintain that in memory, and that can actually end up, costing a lot of memory when you're doing garbage collection. And finally, we do have to stop the world before we start marking because if someone is like going ahead and around and fiddling with the fields in our program, well, that doesn't work so well. So we're going to talk about another algorithm which lets us fix this problem. But any questions about mark and sweep before I keep going? Okay. So we're going to try to fix these four problems. And the fix for this is what's called copy and collection. Copy and collection is a very popular technique for garbage collection, and it's used in a lot of languages where you don't need very close FFI support. And we'll see why that's the case in a moment. So the idea behind copy and collection is instead of marking objects that are live, we are instead going to move them. We're going to copy them over into another region of memory and use that to sort of keep track of what needs to be scanned versus not. So in this picture, I've got a from space and I got a to space. The from space contains all of the memory that like was in use and I'm now trying to garbage collect. And the to space is expected to be entirely empty, nothing in there. So how do I do this? So what I'm going to do once again is I'm going to start off by traversing the root set. When I get to the root set, I see that A is reachable, so I copy it into the to space, and now I actually don't do anything else, right? So previously I had to maintain this to-do list saying, hey, here are the things I have to do. But with copy and collection, the to space is actually going to serve as our to-do list. We're going to keep track of how many objects in the to space we've actually already scanned. So right now I haven't scanned anything. So now that A is in the to space, I have to scan A. And A's fields still point at the old objects in question. So let's go ahead and do that scan, right? So I need to scan A, and by scanning A, I see that it points to B and it points to E, and similar to what I did for the root set, I just go ahead and copy them into the to space. So here I go with B and E copied in, and once again, right, I've only scanned A, I haven't scanned B or E, so I need to, scan those very shortly. But now A's pointers get updated to point into the to space. So, A's happy, I don't need to process A anymore. So I go ahead and do that again for B, right? So B points to D, so I go ahead and copy D in, and now B gets updated to point to the copied version of D. It's scanned. E doesn't have to do anything, and D doesn't have to do anything. And now I'm done. And so literally what I do is, once again, I've done this graph traversal. I've copied everything that's live, and then I can just unceremoniously delete the entirety of the from space. In practice, I'll just, forget what is stored there and go ahead and start allocating out of that region. Copy and collection has a lot of benefits. So sort of by its nature, it copies from one end to the from space to the to space. And in doing so, it compacts all the data together into one space. So that's better locality because your data is closer together. You're more likely to get a cache hit in that case. And it also means that we don't need any extra bookkeeping. We don't need that to-do list that mark and sweep collection needed. The to space does that automatically for you. Of course, I'm a little cheating when I say that, right? Because like what I had to do is I had to say, well, whatever it is that you're doing in your application, you need twice as much space to do copy and collection because you need that, to space, which needs to be clear as you're doing the copy in question. So you basically have doubled your memory requirements. That's not a big deal like in server applications, but like on mobile, that can be kind of killer because you just don't have that much space to begin with. And of course, to do copy and collection, it's still necessary to like stop all the mutations so that you can go ahead and start doing all this copying business. Because it would be really bad if someone was like still on the old A and modifying it and we didn't see this change because we'd already copied it over into the to space. Okay. So garbage collection, what does it do? It provides the illusion of infinite memory. Liveness is based on reachability, right? Because that's the easiest thing to do. And there's one more thing that I didn't talk about, which is this concept called generational GC, where the idea is, in all of our tracing garbage collection things, we had to trace over the entirety of the live data in our heap. And if your program has been running for a very long time, there might be a lot of live data that you need to traverse over. And that can take a lot of time to basically conclude that, all of this is still live, nothing to do. So the concept behind generational GC is it says, well, objects that were allocated recently are more likely to die sooner. That's what's called the generational hypothesis. So what you do is you just spend a lot of time garbage collecting the new stuff and you don't bother touching the stuff that's old. And that's cool and it's a cool idea, but it's actually quite difficult implementation wise to get this working correctly because in order for it to be okay to only scan the new objects and not the old objects, it must be the case that there's no way to point from the old generation into the new generation. And of course, in most programming languages, you can mutate objects, and so that invariant doesn't necessarily hold. So you have to do a lot of work to make sure that you don't get tripped up when that happens. Okay, that's everything I wanted to say about garbage collection. Any questions? I said I was going to be fast, but I ended up taking up half of the lecture talking about this. Any questions? Questions? A fun thing that I want to mention is sometimes you don't have a root set. So I was recently working on some stuff related to Python's garbage collector, and Python actually does not have a root set. Okay, it does, but it doesn't require a root set to be defined for an object to be live. What do I mean by that? Well, so Python has very close interoperability with external systems like C. Like a lot of things in Python are written in C, and basically the problem Python has is that when you have a bunch of opaque C code, that C code could have owning references to Python objects, and your garbage collector doesn't necessarily know about those references. So how the heck can Python do garbage collection if it doesn't even know what all the what the root set is? And the answer is it figures it out on the fly. So what it does is it first does a traversal over all of the objects in your heap, and it says, hey, what's reachable from you, and it basically does all that, and then once it's figured out all the objects that point to each other, it now knows, okay, here are all the reference counts that I know about, and then anything that I didn't see, like any unexplained higher reference counts, those correspond to external references in, and so they should count as being in the root set, and I shouldn't deallocate them because something that I don't know about is holding onto them. That's a fun little tidbit. Okay, so let's move on to the virtual machine portion of this lecture. Now, I say virtual machine optimizations and just-in-time compilers, but really what I'm going to focus on is a very important question, which is how do you make dynamic dispatch fast? So we already saw one answer to this, right? So in C++, the way we make dynamic dispatch fast is by making it compile to a very small amount of code, right? So when I do a virtual method call in C++, all I do is, I do an offset into the vtable, and I dereference the pointer there and just jump there. And C++ basically asked itself, what is the bare minimum work I can do in an ahead of time compiled setting to actually do this virtual method call? So C++ did that. And as a result, we get lots of interesting things like, the diamond problem and, virtual-based classes and all that stuff. Because C++ was like, I really, really want this code to work, and I will do whatever it takes to make it happen. There's a comment in the chat, which is, could you say it's trading runtime lookup for compile time lookup? Let me think. Well, there is some amount of compile time lookup going on, but I'm not sure I would say that necessarily. What's more going on is, in order for C++ virtual tables to do minimal effort at runtime, C++ had to make UX decisions. It had to change the semantics. Well, I guess it was defining the semantics. It had to define the semantics of its language in such a way so that the runtime behavior could work this way. And so, for example, Java has this concept of an interface, right? An interface is some, it just says some methods which are supported by an object, and then any object can implement the interface along with as many interfaces as it wants. And this is nice, and it makes sense, and Java programmers love interfaces, and C++ just can't give interfaces, right? C++ can do multiple inheritance, which is kind of similar, but multiple inheritance is just, sort of slapping together multiple copies of the vtable pointer for every interface that you want to do. And then all of this pointer offset nonsense. This concept of an interface is just not efficiently implementable in C++, and so they don't offer it as a concept because, can't implement it. Does that make sense? So let me give one particular problem with C++ virtual tables, another one. So let's suppose that we've got these two classes, and class A defines F and G, and class B defines B and F. And I want to be able to do a virtual call between the two somehow, referring to F. And so clearly in C++, this doesn't work so well because in the case of A, F lives in the first slot. In the case of B, F lives in the second slot. And so if I want to write a single piece of code that can work in both cases, well, I can't, right? Because they just have totally different locations. And I would have to do something like multiple inheritance to just have multiple vtables, one for every single layout that the user wanted to do. So obviously, you have the same problem when you want to implement virtual calls in a dynamic language or like a not C++ language. And a very common way to solve this problem is just have a dictionary, right? So if you have a dictionary, this isn't a big deal because you just say, okay, well, I've got a map from F to the function and a G to the function. And so I don't care what order they're implemented. I can just go ahead and do the hash table lookup to find a thing in question. But hash table lookups are pretty expensive. So it's not a great solution. And like if you did your JavaScript interpreter in this way, like it would just run way too slow for anyone to actually want to use it. So, right. So C++ says you have to do both layouts, right? You have to have two vtables to actually make it work out. And the idea behind Java and most VM languages is we are going to do this inefficient dictionary lookup at some point. But then we're going to cache this result. And by caching this result on subsequent accesses to the virtual method, they will go fast. And that's our idea, right? So we don't need to like solve the insoluble problem of having a single binary interface that can work no matter what. We'll just like do the slow thing and then make it fast on subsequent calls. This is sort of like the name of the game with just-in-time compilers. They're all about making assumptions that like ordinarily wouldn't be sound, but then being able to go fast when the assumptions are okay. So we're going to talk about the virtual machine. I need to do a brief segue into how JVM bytecode works because I need to explain how JVM bytecode works to talk about what optimizations JVM does. So basically, we talked about the virtual machine as a black box, but actually it contains a bunch of components. So it contains a bunch of components because, well, it has to do a bunch of stuff, right? So you give it some bytecode to run, and then it actually has to go ahead and load that bytecode as well as the bytecode of any libraries you might use. That's what the loader does. Then the JVM has to verify that the bytecode is valid. That's because the JVM hypothetically is supposed to be usable in untrusted contexts. Like you can pass, in practice, no one ever uses Java in this way, but like on the web, right? The VM also needs to like check that, well, you don't send bytecode. Okay. Like for WebAssembly, right? One of the things you need to do is you need to check the WebAssembly is actually valid. And, so there's a verifier that actually goes ahead and does that. And then we have to actually go ahead and link, all of the bytecode together. And then finally, there's the just-in-time interpreter that actually does all of the stuff in question. So the VM, actually has a bunch of pieces. And one more thing is, what is JVM bytecode? So JVM bytecode implements a stack machine. So if you showed up for the Torch Dynamo live stream, or if you remember your I think it was your second homework in Haskell, you implemented a stack machine for a calculator, right? How did a stack machine work? You had a stack, you pushed arguments onto the stack, and then you ran operations which popped some number of arguments off the stack and then pushed the result onto the stack. Well, JVM is also implemented as a stack machine. So here is some example bytecode in JVM. This is implementing F inside this class A. And what is it all doing? Well, what does it say? It says, okay, first load the argument representing to the this object, that is to say the self object in the method call. So that gets put onto the stack. Then load the load the argument val, the first argument as an integer into the stack. So now we've got a stack with 2 elements on it. It's got this, it's got the value of val. Load a constant 1 onto the stack. So now we have 1 on the stack as well, 3 elements on the stack. And then iadd says, hey, go ahead and pop the top 2 arguments on the stack, which is that constant 1 and the value of val, and push onto the stack the result of adding these 2 together, aka val plus 1. And now put field number 4, aka filled and basically says, okay, take the top 2 arguments, one of the arguments being the value you want to fill in, and the other argument being the object you want to fill in, and go ahead and actually write in the value into that field on the object in question, and then finally return, right? So we're going to be primarily interested in this operation, which is actually interacting with the objects in question. But that's how JVM bytecode works in a very short explanation. Okay, so we want to talk about dynamic dispatch, and there are 3 bytecodes in the JVM for doing dynamic dispatch, and it's very nice because we can talk about different implementation techniques for each of them. So going in order of complexity, we're going to talk about first invoke virtual, which is just what happens when you call a method on a class that may have subclasses inheriting from it. Then we'll talk about invoke interface, which is what happens when you call a interface method. So you have an interface object. You have an object that's you have a object, but you don't know what its type is. All you know is that it implements an interface, and that sort of situation gives a different bytecode called invoke interface. And so that's going to also need a different strategy for compilation. And then finally, we'll talk about invoke dynamic, which is used in sort of more dynamically typed programming languages. Actually, Java itself doesn't have much use for this, which can handle a sort of very dynamic situation. Okay, so let's start. So what does invoke virtual do? So invoke virtual says, I've got an object which is got some type A, and I'm going to call a method on it. And every method call in Java is virtual. So any method call is going to look like an invoke virtual. And just to recap for a moment, in C++, right, we had a vtable, and so when we compiled the class, we had this fixed vtable layout, and then we had some code which referred to a specific location in the vtable. And if you, for example, change the order of the methods in the class in question, you had to go ahead and recompile the client code to work for the new binary layout in this case. So there's this dependency between the interface and the implementation. Now, in Java, Java has a goal of what's called separate compilation. So separate compilation in Java says that I can compile my class definition and my use of the class definition separately, and I don't have to recompile my use of it if there is not a substantive change in the class definition. So in other words, when we type check our code, we type check against this interface, and then when we provide some bytecode, we verify that the bytecode implements the class in question, but we don't actually require you to recompile the target code if the verification is still valid. And so if I modify the class in question, there's a typo in this slide, which is I was supposed to reorder the methods. If I modify the interface, the class might get slightly different. But so long as the bytecode for my client verifies against the new class in question, I don't have to recompile in this case. And clearly that strategy that I used in C++ of just hard coding in the index, that's no good, right? That won't work if I don't want to recompile. And so invoke virtual will actually just go ahead and record the entirety of the method name that I want to call. And so some extra resolution process is going to figure out what it's calling. So how exactly do we run this? Well, on the first time, we're just going to go ahead and look up the element, in a.class, right? So a.class does have a layout for its methods, and it says, okay, bar is 0 and foo is 1. And we can just go ahead and do the hash table lookup to find the index corresponding to foo in the situation. And once we found it, this choice is always valid no matter what the for the rest of the execution of this particular program on the JVM. So actually what I can just do is I can replace this bytecode with a optimized bytecode, invert quick, which just says, okay, don't bother doing this lookup the next time. Just go ahead and just go and look at the first field of the vtable for a.class in this case. So the big idea, right, is that like if I've got some bytecodes and they require me to do this slow computation to figure out like what they actually want to do, but that computation stays the same throughout the entire execution of this process. And that's true for old-fashioned virtual objects methods on Java classes, because actually Java does have an internal notion of a vtable. It's not going to gratuitously reorder methods within a single invocation of our process. So the location of a.foo is always going to stay the same. So we can do this portable bytecode, which is indifferent to reordering of the vtable, but then when we actually run the code on the JVM, we can just go ahead and update it to actually hard code the real thing. And because we're updating the bytecode itself, there's no like extra conditions that I have to do in the interpreter to check a cache. The next time I execute the code in question, I'm just going to execute the invert quick bytecode, and like literally nothing else had to change. There's no actual lookup in a cache. And that's really important, because like having to ask the cache, is there actually something here or not? That can be a big time waster. And when you just modify your code in this way, you don't have to actually do that. You just piggyback off of the normal interpreter loop in your VM that is like going through and figuring out what to do by looking at the bytecode in question. Okay, so let me just pause a moment and recap something that I said, which is that when I do this, I am assuming that there is a layout for the methods on the class, and that I can figure out what the index is, and that index will always be valid for not only objects of type A, but subtypes of A. And that's okay because Java doesn't support multiple inheritance, so Java can just make sure that all the vtables are laid out consistently for all the subclasses. But because Java doesn't support multiple inheritance, it supports something else instead, which is interfaces, which can be implemented multiple ways. And so we've got an analogous problem when we want to make a method call where A is in fact an interface rather than a method. Sorry, interface rather than a concrete class. And so I would like to do this interface rewrite, but there's not a single rewrite that is valid in this situation, right? I could have an implementation of the interface A, which orders foo first, and I could have another implementation which orders foo second. And what we said, you had to do if you were doing C++ would have been for every interface, we have to compile a separate vtable in a fixed order so that I can use that vtable to do the operation in question. And so we ended up with lots and lots of vtables. But this is Java. We've got a just-in-time compiler, so things are different this time. We don't have to suffer through all of this. So our idea is that although you can write very polymorphic code in Java, in reality, the code is often not that polymorphic. When I'm running this actual code, there's usually one particular object that I run up against all the time. So the idea is that I'm going to do a cache, but this cache, I actually need a little bit of extra information, right? So the original cache was unconditionally valid. This cache is going to be a little different. It's going to be like, if the class that you're invoking this method on is B, then I know exactly where it is and I can do a direct invocation. And so this is the fast path. And otherwise, if I don't know what it is, then I have to do the slow path. I have to go do the lookup and find the thing in question. And so the idea is that that we don't actually have to write this if statement inside of our code. We can instead just store this directly inside of the bytecode instruction itself. So the big idea is we're going to rewrite our bytecode like we did before, but we're going to store the result of the cache lookup directly inside of the bytecode along with the condition saying whether or not it's valid or not. So instead of having an unconditionally correct rewrite, we instead have this rewrite which we have to basically check if the class matches. But if the class matches, then we're happy and we can just go straight to the destination without doing a slow interface invocation. By the way, there's some stuff we can do in a just-in-time environment that we can't do in an ahead-of-time environment. So let's say that we're running our program and it turns out that we never actually have any other implementations of the interface. B is the only implementation of the interface. Now, in principle, there could be arbitrarily many implementations of an interface, but at this particular point in time, when I'm running the VM, it might so happen that there's only one implementation. So this is called the singleton class situation. So in this case, we actually don't even need to save the conditional here, right? Because as long as we don't load another class that like has another implementation of foo, we know this has to be the one that we're going to call, and we don't even need the conditional in this case. So it's a nice optimization that you can only do at runtime when you know exactly all of the code you've loaded, because in principle, someone else separately could compile some foo, and you would never know about it until that code was loaded. So you can basically make tons of assumptions, and as long as they happen to be valid at the time, those assumptions will never get broken on you. And all you have to do is make sure you just like roll back those assumptions if someone, say, loads some new code, like dynamically loads a new class object that invalidates those assumptions. And that's what class hierarchy analysis in Java is doing. Okay. Questions so far? I'm almost done with the slides. I'm running up against time, but I want to see if there are questions. So just to recap where we've been so far. So we talked about invoke virtual, right? Invoke virtual was easy to optimize because the transformation we wanted to do was always valid. But we only would know how to do it when we were actually running our VM and when we actually like saw the code and saw, okay, here is where they happen to have put the object. So you just go ahead and rewrite the bytecode. It's super easy. It's super easy, and like you can do this in a lot of situations. The second situation is where you want to do a rewrite, but you're not sure if it's always going to be right? And so what you can do is you can rewrite the bytecode into some conditional one, which checks if the fast case is valid, and if it isn't, use the slow path, right? So it's still valid, and you can also make assumptions that happen to be true at the time, as long as you invalidate them when those assumptions get broken. And so the last idea is what's called invoke dynamic. And so in dynamic languages, when you do calls like to plus, there are probably, there could be a lot of different objects that you get run in this case, right? Because it's a dynamic language, so there's not necessarily like a single type that a particular object has. And so the idea is, well, if a one place cache was good, a many place cache is even better, right? So the way a polymorphic inline cache works is we start off with only the slow dynamic lookup handler that like just does the slow path, finding the object using a hash table lookup. Then the first time we run this code and we say, oh, the object at this point in time happened to be A. Well, we're going to go ahead and rewrite this code so that we have an if statement testing if A is the class. And if it is, do the fast path for A, right? And then if we happen to run this code again, and the next time we notice that the object in question is a B, then we'll just add another if statement, this time testing if the class is B. And if it is, go ahead and invoke the B handler in that case. And we'll do this as many times as we're willing to do. There's usually some policy about how many entries in the cache you're allowed to have. And we can also do things like, if A is called a lot, then we want to make sure that it shows up first in the if statements so that we usually hit the right thing right away rather than having to do a bunch of tests. And then that's it. That's all there is to polymorphic inline cache, right? If you bought into this idea that modifying your code, modifying your bytecode, or sometimes modifying your actual x86 machine instructions is a good idea, you can do these optimizations, and they're very simple to do, and you actually can get a ton of performance improvement. So the idea for polymorphic inline caches, they come all the way from Self. Remember Self? Self was the prototype-based language that JavaScript's design was designed on. And I mentioned that Self pioneered a bunch of VM techniques, and picks, as they're called, came from Self. And so when they did picks in Self, it actually improved the performance of their programs by 37%. So that's a huge improvement for just a simple mechanism like this. Okay, so to summarize, what is the big takeaway you should take from JITs? And I think the big takeaway you should take is JIT, just-in-time code generation, gives you flexibility. It lets you write source code that would have been wildly inefficient if you had to ahead of time compile it, because you have no idea how to actually ahead of time compile it. And you say, well, yes, if you're trying to handle the situation, no matter what, it is going to be difficult to generate good code in this case. But a just-in-time compiler doesn't have to handle situations in their full generality. They can specialize for what actually happens in practice, and that lets you go faster. And there's a question at the beginning of lecture, which is, are interpreted languages slower than compiled languages? And then I was like, yeah, most of the time they are, because a compiled language does a ton of more work ahead of time. But this is not universally true. Sometimes a just-in-time compiled language can be faster than an ahead-of-time compiled language because of this aggressive specialization, because of the assumptions that it can make. Okay, that's everything I wanted to talk about today. I'll stick around for a minute or two if there are any more questions. Otherwise, see you all next week.